Welcome to The Explainer. For a lot of people, Calculus 2 feels like this random collection of tricks and theorems. But what if I told you there's a single, powerful story that ties it all together? Well, today we're going to uncover that exact narrative and see how everything just clicks into place.
So, what is this big story? Well, it starts with a really basic question. How do you find the area under a curve? But from there, it launches us into mastering the mind-bending concept of infinity. And it all leads to one of the most beautiful ideas in all of math, being able to rewrite almost any function you can think of as a simple infinite sum.
When you really boil it down, this entire subject is built on just two foundational concepts. First, the idea of accumulation, just adding stuff up. And second, the careful, rigorous way we have to handle infinity. Everything else you learn, it's just a tool designed to serve one of those two big ideas. So let's kick things off with the first one.
The story of Calc 2 really begins where a lot of calculus itself began, with a simple, almost practical problem that had mathematicians scratching their heads for centuries.
Think about it. Finding the area of a square or a triangle, easy. But what about the area under a curve, like a parabola? You can't just multiply length by width. This is the classic area problem, and solving it required a really, really clever strategy of approximation. And that strategy is what we call a Riemann sum, and it's actually beautiful in its simplicity. First, you take that complicated, curvy area, and you just slice it up into a whole bunch of thin little rectangles. Rectangles you can easily measure. Then you just add up the areas of all those simple shapes. Now, is it perfect? No, it's an approximation, but it's a fantastic start. But here's where the magic happens. You start to ask, okay, what if we make those rectangles infinitely thin? As you do that, as their width approaches 0, all that little error you had just vanishes. It disappears, and you're left with the exact perfect area. This limit, this exact number, is what we call the definite integral. It's the perfect measure of total accumulation.
Now, for a really long time, this whole method of finding areas was seen as being completely separate from the other half of calculus. They were like two different worlds.
So on one side of the street, you had Calc I, right? The world of derivatives. It's all about finding the slope of a curve at one single point, that instantaneous rate of change. And then way over on the other side, you had this new world of integrals, which was all about summing up an infinite number of tiny things to find a total amount. They really seem to have absolutely nothing to do with each other.
And then, boom, one of the most profound discoveries in the history of science happens. The fundamental theorem of calculus. And it didn't just connect these two ideas, it showed that they were actually just two sides of the very same coin.
And this right here is the absolute key. The theorem proved that integration is just the exact opposite of differentiation. So instead of doing that complicated infinite sum, you could find the total area just by asking a much simpler question: what function, when I take its derivative, gives me this curve? Finding that original function, the antiderivative, was a massive, game-changing shortcut. It was like a cheat code for mathematics.
This incredible discovery completely flipped the script. All of a sudden, calculating areas wasn't really about limits and sums anymore. It was about getting really, really good at running the process of differentiation in reverse.
And because of that, mathematicians developed this whole toolbox of sophisticated techniques. So methods like U substitution and integration by parts, they're like specialized wrenches, each one designed to find the antiderivative for a very specific type of problem.
But what's so cool is that these techniques aren't just random tricks somebody made up. No way. U substitution is literally just the chain rule run backwards. Integration by parts, that's the product rule but in reverse. Every single one of these techniques is a logical consequence of the derivative rules you already know.
Okay, so we've got this powerful toolbox for accumulation. We're feeling pretty good. So what do mathematicians do? They start asking bigger questions. What happens if the thing we're trying to add up goes on forever? This is what pushed these ideas to their absolute extremes and brought us to the second major theme of the course: infinity.
And this is where we enter the truly fascinating, sometimes really weird world of infinity. What if the area you're trying to measure just stretches on forever? Or what if you try to add up an infinite list of numbers? Can you even get a real answer from that?
The whole game changes here. The question stops being, what's the number, and instead becomes, is there even a finite number at all? If an infinite process actually settles down to a specific final number, we say it converges.
If it just blows up to infinity or maybe bounces around forever without settling, we say it diverges.
And this slide shows one of the most beautiful parallels in the entire course. Check it out. The rule for when an improper integral of 1 over x to the p converges is identical to the rule for an infinite series of 1 over n to the p. This isn't a coincidence. It shows this deep structural connection between adding up a continuous function and adding up a discrete list of numbers. The logic of infinity is the same in both worlds. It's amazing.
So all of these skills we've been talking about, mastering integrals, understanding infinite series, developing all these tests for convergence, they've all been building toward one of the absolute crowning achievements of calculus. This is the grand finale.
And that finale is the idea of a power series. Think about this. What if you could take a really complicated function, something messy like sine of x or e to the x, and rewrite it as something incredibly simple, like a polynomial? The only catch is that the polynomial is infinitely long. I mean, how powerful would that be?
Now, this infinite polynomial isn't always a perfect substitute for the original function. The big challenge, the final boss, if you will, is figuring out for which x values this magic trick actually works. That special domain is called the interval of convergence, and finding it takes a really careful multi-step process. And this is how it all comes together. It's like the ultimate final exam. You start with a super powerful tool, the ratio test, to find the main chunk of the interval. But that test always fails right at the boundaries. So, to figure out what's happening right on the edge, you have to pull out every other convergence test you've learned. The p-series test, the comparison tests, they all come roaring back. It's the ultimate synthesis of everything we've done with infinite series.
And that's the whole story, right there. We start with a very concrete problem, finding an area. We discover a deep, profound connection between accumulation and rates of change. We build a whole toolbox to take advantage of that link. And then we push those ideas all the way into the realm of the infinite, only to discover that even the most complex functions in the universe can be built from the simplest possible pieces. It's a journey from the finite to the infinite and all the way back again.